Hello, this is going to be a video lecture. Last time we talked about feed-forward neural nets, starting with perceptrons and then going to multiple layers. And then the training was due to the error backpropagation. So that's really more computer science. I mean, the previous topic of feed-forward networks is kind of like computer science. There's not a lot of physics content to that. But that's different for today. So today we're going to look at a Hopfield recurrent network. And this actually turns out to have come out of a strong analogy with something known as a spin glass, which is a solid state system. And there is something called a spin glass Hamiltonian, which relates to magnetic interactions between spins. And it turns out that it maps right onto a description of a neural network. And this was noticed by John Hopfield, and so this is why this is called a Hopfield network. So he was a solid-state physicist who got into biophysics and then saw this really strong analogy between these spin glass Hamiltonians and solid-state and this neural structure which does associative recall. And so the Hopfield recurrent networks specifically do associative memory, and this is where you store ideal memories, and then you present the network with some kind of a noisy version of that. And it can be pretty noisy. And what the network will do is it'll actually converge on or recall that memory. So we'll do a little bit of physics today, and it involves Lyapunov's theorem. Also involves what's called basins of attraction, which really means that we have stable attractors that are attracting the network dynamics. And then we'll talk about the operation of these networks, the training, which is really more of a storage, and then recall, which is a retrieval phase. So this is a general example of a what's called a recurrent or a feedback network. In this case, it's multi-layers. It'll have it's just two layers of neurons here. You can have inputs coming from outside. These neurons, in principle, can feed back to themselves, and so there are these closed loops. So this is a general architecture, but this is not the specific Hopfield. So this is general, but now this is the Hopfield network. So the Hopfield network has several constraints, and the reason for this is that it's to preserve this mapping of the spin glass Hamiltonian onto the neural network structure. And so in this case, there's really just a single layer of neurons, and you start them out with an initial state. And so, well, first of all, okay, there's going to be a storage phase. Now, the storage phase has all to do with the synaptic weights, the WIJs. And so each of these inputs is going into one of these artificial neurons. And so then there's going to be a summation taking place, and then also a response function. And then the summation will be weighted by these synaptic weights. So the training or the storage part is all about setting these synaptic weights. Then to launch this, what you do is you just give it some kind of an initial state that is just some random state of, in this case, it would be 4 values. And then these go and then get fed back into the whole, all the networks, or all the neurons. Now there's all-to-all coupling, but there is no self-feedback. And so you'll notice that, for instance, this output here from the first neuron actually comes out, and it misses. There's no connection there. So it'll actually feed into the second, third, and fourth, but not into itself, and then vice versa for all of these. And so there's no self-feedback, but it is all-to-all coupling. Now, it does require what's called asynchronous updates. So these have to be iterated in time steps, and at each time step, what you do is you randomly update one of these neurons. The reason to do that is that if you have some kind of a continuous dynamics, neurons or networks like this with feedback loops can actually oscillate, and so you can end up with a lot of limit cycle oscillators. And the goal is not to have limit cycle oscillators, but actually to have convergence on stored memories inside of the network. And so with the asynchronous update, and I'll give examples of that, you iterate this over time until it converges. You actually hit a steady state where the output feeds back onto itself and generates the same output, and so that's the fixed point. All right, so let me just remind you about the artificial network or neuron structure. And so there's a summing junction, you've got the inputs, and then you've got the weights, and then there's this activation function, which is always some kind of a sigmoid. Now, it turns out that a very convenient sigmoid for doing theoretical derivations is the hyperbolic tangent. And so the hyperbolic tangent is a smooth step function, but it does have a gain parameter. So as this gain parameter increases, the step function will get steeper and steeper. Now what's nice about the hyperbolic tangent is, so here's the activation function S, is that it has a well-defined and smooth inverse. And so the inverse of the activation function is actually this nice smooth function here, goes as a logarithm. And then this has a positive derivative everywhere. And so it actually starts out at infinity, goes to some finite values, and then goes back to infinity in the limit. And so it's always positive. And so it turns out that the derivative of this, in fact, that's actually what I meant to say, the slope is always positive. So the derivative of this inverse response function is always a positive number, and that's going to feed into what's called Lyapunov's theorem. Lyapunov's theorem is going to be something we invoke to show that there are stable fixed points that represent a perfectly recalled memory. So Lyapunov's theorem is kind of abstract, or when you first read it, it doesn't sound like it says a lot, and I'll just read this off. So for a state vector x sup a in an equilibrium state x bar, and so that would be the fixed point, the equilibrium state x bar is stable if in a small neighborhood of x bar, sort of a small neighborhood of that fixed point, there exists a smooth positive definite function. So positive definite just means it's something which is always either positive or limited on the low side by 0, such that the time derivative of this positive definite function of the coordinates, or the state vector, equilibrium state vector, is going to be less than or equal to 0. And this is for all the x in the neighborhood of the fixed point. So all this is saying is that I'm going to construct some kind of a function which is positive everywhere as a function of the state vector. And if the time derivative of that positive function is negative, so in other words, it's always decreasing. So it just, as time goes on, this positive definite function just gets smaller and smaller and smaller, then this is going to be a stable fixed point. So that's Lyapunov's theorem. So let's apply that to an artificial neuron. And what we're going to do is put this into the form of an energy function. So energies can be constructed so that they are always positive. And so the energy function is going to be this double summation over the synaptic weights. And so then here are the state vectors, but we're looking at all possible combinations of state vectors. This actually is just like a Hamiltonian that shows up in magnetic systems. So when you have spin systems or magnetic moments that are interacting, these x's are actually like the spins, and this is like the exchange interaction that tells you whether the spins are going to align or anti-align. So this actually is it's a spin Hamiltonian that comes out of solid-state physics when people are studying magnetism. And so it's also then the synaptic weights coming in on and weighting these state vectors. And so that's sort of the analogy that John Hopfield noticed in 1982. And so also there's some additional terms that we can add in here to guarantee that this is a positive definite function. This is that inverse activation function. Again, kind of working with this thing as if it were an equivalent circuit. So here's resistance. Here's the output function. Here is the current. So what we do is we want to take a time derivative of this. And so we'll take a time derivative and distribute that through all these terms. And what we'll get is this expression. And so I've already distributed out this common factor in front of the dxb dt. And you'll immediately recognize that this is the local field. This is the output of the summation junction. And so we can rewrite that then as the capacitance times the derivative of this local field. And so here we've got a dVb dt, but that is going to be this inverse response function. And we can then distribute that in terms of a d by dt becomes a d by dx, and then a dx by dt. The dx by dt turns this into a square. So now we've got a quadratic, which is positive definite. Here we now have the derivative, because we have the d by dx on this inverse response function. And so if you remember, this was always having a positive derivative. So here's something which is always positive. Here's a square which is always positive. That's just the capacitance, which is always positive. And lo and behold, there's a negative sign in front. It actually kind of came through from the whole beginning. And it isn't smoke and mirrors. It isn't magic. What it's showing is that in this formalism, where we construct this positive energy, the time dependence on that energy is always negative, meaning that the energy is always decreasing, and then it's going to decrease until it hits the fixed point. And so this is really, in terms of spin glasses, you're really describing a system which has a potential energy landscape with a lot of local minima. And if you start somewhere on a slope in this landscape, you're going to go downhill towards that minimum. And so you really think in terms of this potential energy landscape with a lot of local minima. And each of the local minima are actually going to be stored memories. And so in magnetism, they're ground states to the magnetic Hamiltonian, but in terms of this neural network, these are going to be the stored memories. And so we finally, oh, there it is actually, it's okay. So here's that inverse response function that had a positive derivative everywhere. And so therefore, we've proven that the energy is always decreasing in this case. And so this proves that by setting up these synaptic weights in an appropriate way, which I'm going to show that in a second, it's going to turn out that this is going to be a projection operator where we're projecting onto ideal memories, then in fact we can have basins of attraction, which means that if we're somewhere nearby an ideal memory, even if we're giving the neural network an input which is corrupted somehow or noisy or partial information, it will converge on the ideal memory, and so it'll be a perfect recall in that case. This is a way of looking at the basins of attraction. This is, again, just conceptual. The state space is a very high-dimensional state space. In fact, the state space is going to be n-dimensional. If we have 100, vectors of 100 elements, then it's going to be a 100-dimensional state space. But just conceptually, there's going to be these basins of attraction so that any point, so here is the basin boundary. And so any point inside of this basin is going to slowly lower its energy until it reaches the minimum in the potential energy. And this is going to be a true memory. And so this is a state that corresponds to the ideal memory. Anything off of that green point is some kind of a noisy input or partial input, but it'll all converge. All these partial inputs within this whole basin area will converge on the ideal memory. And so then there's going to be this boundary. Now the boundary can actually be fairly rough, and in high dimensions, in a 100-dimensional space, you could actually have very jagged boundaries. And so that if you're right near the boundary, just a little change in the noise might actually kick you over into another basin, and so that you'll actually go to the wrong memory. And that does happen. If your inputs are corrupted too badly, then the system is not going to be, easily know what the correct memory is. And so a little bit of noise, may make it go to this memory, or a little different noise will make it go to that memory. But certainly they won't go to this memory down here. So they're still going to stay somewhat local. Now I do want to point out that this is actually a false memory. And so when you train these networks, you'll train it with m memories, but because n is a lot larger than m, so n is the size of the state vector and m is the number of memories. Because the size of the state space is much larger than the number of memories, there's another proof that we won't do that there have to be false memories. There have to be fixed points that are not part of the stored set of memories. And for instance, this would be a false memory here, so that if we have some kind of a corrupted input, maybe we were looking for this recall here, but there's some kind of a corrupted input that pops it over to this other basin, and it's going to go to this false memory. And that's going to be a memory which was never programmed into the network. It turns out that there can be a large number of false memories. They do only come up in the case of strong noise, because typically what we're doing is we're looking to present information to this network which is close to some of the stored memories. And so the input would have to get pretty noisy before we would actually start to run into problems of getting these false memories. All right, so there's two parts to working with a Hopfield neural network. There's what's known as the storage phase and then the recall phase. So the storage phase is straightforward. So we're going to talk about M fundamental memories. The state vector is going to have a length of n, so there's going to be n components to the state, to each state vector. And so here is a fundamental memory. So mu means that this is the muth fundamental memory, and this is the eighth component of that. So this is just a vector, and there's going to be m of these vectors. So now the synaptic weights are constructed as outer products. And it's a little, I mean, it's been a while since we've looked at the, the index notation where we've got, superscripts and subscripts. And then this is a little bit confused by the fact that we've got this additional index, which is the memory, the muth memory. So ignore these mu's, and what you've got is a contravariant vector and a covariant vector. And so then this is an outer product between these two fundamental memories, or actually, sorry, it's the outer product of the muth fundamental memory. And so then what we do is we sum over all the fundamental memories, and so we create this outer product of each of these fundamental memories. And then we also make sure that the diagonals are 0. This is because there's no self-feedback. Now it also turns out that to make sure that the dynamics really do converge on the fixed points, we have to actually subtract off an average value, and that's what this is here. And so this is just the identity. It's not the current. It's the identity matrix for m memories, and we've got n elements of the vector. So subtracting this off just allows us to converge onto the fixed point numerically. So this outer product is actually a projection operator. And so one way, so I'm going to make an analogy with quantum mechanics. So a projection operator in quantum mechanics is constructed like this. So you've got actually the bras and the kets. And so here's the, actually this is the bra, this is the ket. And so you construct this projection operator. And the way that it works is, let's say we've got some kind of a mixed state coming in. And so this is a quantum mechanical mixture. And we've got A times this is an eigenvector plus, this is just little b is the coefficient of an orthogonal eigenvector. So A, capital B are orthogonal. So when you apply this projection operator onto this wave function, the inner product of A with B is 0, but the inner product of A with itself is 1. And so we actually pull out the coefficient A. And so that's why we're projecting that this wave function is projecting with a coefficient of A onto the A eigenvector. And so this A then is telling us what fraction of the wave function is composed of the eigenvector A. And so this outer product is exactly what's going on here. And so this outer product here is a projection. And that's how the Hopfield network works, is you're really taking an input, which is some noisy version of a fundamental memory, and you're projecting onto the memories. And one of these coefficients will be largest. In other words, I can actually, in my noisy input, I might actually have a mixture of fundamental memories, but the coefficient in front of the ideal memory should be the largest. And so the way that the dynamics work is that the largest coefficient tends to win, so that when you do the projection, the coefficient in front of the ideal memory should be largest, and then as you iterate the network, then this just gets larger and larger and larger and eventually converges to unity, so that eventually you've converged right onto the ideal memory. So you start out with a projection that gives you a partial recall, and then it self-reinforces itself as it iterates the dynamics. This is just an example of a state vector that has 120 elements. In fact, I'm going to run a Matlab demonstration in just a second that's going to have 120 elements in the vectors. And so, so it means that the outer product between all the fundamental memories is going to be a 120 by 120 matrix. And so these are this is the outer product matrix in a training set. And it's just color-coded, so that's reds are large positive values, blues are large negative values. It is symmetric. You'll notice that it is symmetric, and also the diagonal is 0. That's all the greens down the diagonal. All right, so that was the training phase. So the training is not really training like the feed-forward networks. The feed-forward networks were sort of an active training process where you had a training set. So in the Hopfield network, it's a little different. You don't view it as a training set. It's really stored memories. And so let me just go back. So that this is deterministic. So establishing these synaptic weights is deterministic in the sense that given the fundamental memories, there's only one way that these synaptic weights come out, and that's this. And so given the fundamental memories, this is the exact synaptic weight matrix that comes out of it. It's totally deterministic. So it's not trial and error. It's a very deterministic and non-random process. Okay. So now the retrieval phase can actually have some randomness to it. Part of it has to do with the asynchronous update, because you're randomly picking neurons to update. So when you run the network several times, you can actually get different answers, especially if you're very noisy on your input and you end up picking up a false memory or a wrong memory. And then you run the network again, and you might actually go to a different false memory or a different wrong, or you might even get it right. And so the operation on the retrieval phase has some randomness to it, but not on the storage phase. So retrieval phase, what you do is you bring in a probe vector. So this probe vector, and A is just the vector index. So this probe vector is going to be a noisy version of a fundamental memory. And you're going to pick that as your initial iterate. So that's iterate number 1. And so you put that into the summation junction of the artificial neuron. And so here's the synaptic weights feeding back on itself. It can have a bias, although typically we will work without a bias. And so then you get the output of that summation junction, and so it's the n+1th output. Now, in the retrieval phase, even though we use the hyperbolic tangent as our activation function, what we'll do for the Hopfield network is we'll give it infinite gain, which turns it into a step function, and so we're just going to take that as the sign. And so anything that's positive will go to +1, anything that's negative, any argument here that's negative will go to -1. And so the infinite gain means that we're going to be working, full binary, just +1, -1. And so this is the n+1th iterate, and then you feed it back in. You get the n+2, feed it back in, or the second, third, fourth. And you keep doing that until you converge, and the convergence is the fixed point. So here is the fixed point. You put in y, and you get y out. And so when that happens, when you put y in and get y out, you've now converged, and you're done. And that's your recalled memory, whether correct or not. Now in this iteration, what you'll do, and I'm going to show that in the demonstration, is that we're going to update the neurons randomly. And so let's just take an example. So here's, it's going to be 3 neurons, and so the state vector has 3 elements to it. So we're in a 3-dimensional state space. There's going to be 2 fundamental memories, which are just given here. One thing you'll notice right off the bat is that these fundamental memories are not orthogonal. In that sense, this is not like quantum mechanics, because in quantum mechanics we like to work with orthonormal sets, and so each eigenvector is orthogonal to all the others. When you're working with memory, that's actually not true. You can have lots of fundamental memories that are not orthogonal to each other. And we still want to try to have a high fidelity network that's going to converge on the right memories. And that's where the feedback comes in. The non-orthogonality means that when you do your projections, you're going to keep projecting onto these other incorrect memories, but as it iterates, the sort of like winner takes all. I mean, the winning projection tends to reinforce itself and ultimately to win. And that's why the iterative feedback is actually allowing us to work with these non-orthogonal fundamental memories. And so that's a little different than the quantum mechanics. So I said that the storage phase is completely deterministic. So what we do is we've got the input vector. So here is the outer product of the first memory. Here's the outer product of the second memory. You divide by the total number of neurons, so it's 1/3. And then this is taking minus 2 memories divided by 3 dimensions on the identity matrix. And so this just makes sure that we don't run into, what would you call it? Well, you don't get these exponential growth or decay, or you don't get exponential growth, I guess. And so you put that all together. So here is the synaptic weight matrix here. It's symmetric, has zeros on the diagonal. And this 1/3 is just going to be participating in the overall numeric factor, although in the end we'll take a sign, and so we'll just be looking for either positive results or negative results. Okay, so let's take a probe which is not one of the fundamental memories, and so this is not one of these. You could sort of say that this is closer to the first memory because I'd have to actually flip 2 of these bits. Or sorry, I only have to flip 1 of these bits to get to this fundamental memory, whereas I'd have to actually flip 2 bits to get to this memory. And so the Hamming, it's called the Hamming distance. How many bit flips you need to go from one binary vector to another. And so the Hamming distance between these two is 1, but the Hamming distance between these two is 2. And so it should be closer to this guy, so let's hope that that's actually what gets recalled. We'll find out in a second. All right, so here's the, this is just this weighting matrix operating on this probe state. And now you'll notice that you get some zeros. And so one of the rules is that when you get 0, that you put it back to the original. And so, so we're operating on this 1, 1, 1 probe vector. And so that's a 0, so this means that this will be, and then when we put it through the sign, this will be 1, minus 1, 1. And in fact that is actually what we get. We get 1, minus 1, 1, and that is this fundamental memory 1. So in fact we were a little closer to that one, and that's the one that did come out. And so once you've got this, you could show very quickly that if your probe is a fundamental memory, you then get the fundamental memory back, and that's the fixed point. Now the random updating, what happens there is that what we could have done, and typically you do when your dimensions are a lot higher, is we would have updated only one of the neurons, meaning that we would have gotten a 1, well, we got 1, minus 1, 1 out. Well, actually, there was no update here, sorry, because we immediately converged on the right answer. Okay, if you have n a little bit larger, what will happen is that you'll get an output, which is a new probe, and it's not going to be a fundamental memory. But what you'll do is you'll just randomly pick one of the neurons to update, and then you'll put it through the system again, and choose one of the neurons to update, put it through the system again, choose one of the neurons to update, put it through the system again. And so then you'll ultimately converge on either a fundamental memory or a false memory. The random updating is important because it is possible to get into limit cycles where you have a probe, you get something out, you plug it back in, and you get the original probe back, or you can even have cycle 2, cycle 3, cycle 4 limit cycles. And you never do actually settle down onto one of the memories, whether true or false. So the random update is called asynchronous updating, and it allows you to converge onto these fundamental memories. All right, so let me give a Matlab demonstration of the Hopfield network. Okay, so here we have a Matlab Hopfield demonstrator. And so what we're going to do is we're going to have a training set, or I probably shouldn't use that, I should call it really a a set of fundamental memories that we're going to store into the network. And then we're going to present the network with a corrupted version of that and see as it iterates whether we can find the ideal memory. And so let's go ahead and run this thing. So it's hop demo. Okay, so these are going to be the fundamental memories. And so there are 128 pixels, or sorry, 120 pixels in each of these images here. And so we've got 8 fundamental memories, 0, 1, 2, 3, 4, 6, 9, and then this pattern here. They're clearly not orthogonal. If you took the inner product of any of these, you're going to get something which is non-zero. The other thing too is what we do is, even though these are two-dimensional images, what we do is we just turn them into one-dimensional vectors, and so we quite literally just read down the rows, right? So we just read down the first row, then the second row, third row, fourth row. So you take the two-dimensional image and you just turn it into a one-dimensional vector with 120 pixels to it. And so you just do that for each of these, and so those become the 8 fundamental memories, and they get stored in the synaptic weight. And then what we'll do is we'll pick one of these, corrupt it with some noise, and then send it through the network. All right, so let's go ahead and use this one here. Let's use the number 4, which is image number 5. So we'll put that there. Okay, so there's the input pattern. So what we're going to do is says enter the probability of flipping a bit. So there's 120 bits involved here. Let's start out simple. Let's make it 0.1. So it'll just be a 10% chance of flipping a bit. So it means that about roughly 10 of these pixels will be corrupted. Okay, and so that's the corrupted pattern. Roughly, we'd have to count, but it is random number generator. But I'd say roughly that's going to be about 10 pixels that are incorrect on that one. And then it just asks the number of iterations to view between each iteration. Let's go ahead and say we're going to look at this every 5. So that's after 5 iterations of the Hopfield network. And so this was input, and after 5 iterations, this is now the output. And you can see that it's cleaned up a little bit. That this is a little bit more recognizable as the number 4. We'll do another series of 5, so that was another 5. And then now it looks like there's just 2 errors at that point. And so then we run it again, and it tells us that after 13 iterations, it hits steady state, and so it stops. So it stops after it hits steady state. And that is the number 4, and so the corrupted number 4. So this was the memory. This is the noisy input, and then this is the recall. And so it's a perfect recall in this case. So let's do it again. Let's just use the same number. We'll do letter 4, which is pattern 5. Let me take a 20% chance of flipping a bit. Okay, so there's the corrupted pattern. Still pretty recognizable as a 4. Let's iterate this every 5. And so there's after 5, 10, 15, and then after 19 iterations, it found it. Now, it is a little bit longer, right? The first time it was 13 iterations. This was now 19. Just for fun, let's just keep going. Hop demo. We'll put in number 4. Let's go up to 30% chance. Okay, well, that's looking pretty ugly now. There's a lot of errors in that pattern, and we're going to iterate this every 5. So that's after 5, 10, 15, 20, 25, 30. After 34 iterations, it actually found it. And this is where you start to get challenging, or you can start to kind of challenge the audience. It's not, I mean, if you look at what your options are, maybe you would have decided that that was the number 4. But if you just showed this in isolation to somebody on the street, I'm not sure that they would know that's the number 4. And so that's pretty corrupted, and the neural network is correctly finding the right answer there. So let's just keep going. Okay, we're going to do the same thing. We're going to pick that number 4. I'm going to go up to a 40% probability. All right, that's looking pretty far from the number 4. Let's iterate in fact, actually, let me just iterate it 10 times, okay? Because I'm not sure this is going to converge rapidly. All right, let's see where we're going. See where it's going. Ah, look at that. So with a 40% corruption, it didn't find the correct recall. It actually found one of the other inputs. So 0 actually was one of the fundamental memories. In fact, let's go back and just take a look. So there it is. And so we had corrupted the number 4, and the network actually converged on 0. So what I want to do is, let me just do it again. I mean, just out of curiosity, let's go ahead and do the exact same thing. It is a random number generator, and so that is a different corrupted version. Actually, maybe a better demo would be where we had the same corrupted input, and you'd see that because of the way that it does the asynchronous update, you can actually converge on a different answer. So we'll do this every 10. So there's something, something, something. And we're done. It's actually converged. So that's the final state. Kind of looks like a 4, but this is a fixed point in the dynamics, but it's not a fundamental memory. And so that is a false memory. So what we've found is that we've got a false memory when we started with this corrupted version of 4. Let's actually do. Oops, what's it doing? Okay, so let's try a different one. Let's see. I think I kind of like 3s and 2s tend to have a lot in common. In fact, if you look at the inner product between the 3 and the 2, you'll actually get something which is fairly sizable. Because like this bar here will actually match that bar, this bar. And so 3s and 2s are kind of commonly mistaken. So let's go ahead and let's put in the number 3, which is pattern number 4. Okay. Let's see, let's go to 30% because 40% looked like we were getting too noisy for it to recall correctly. So let's go to 30%. So there's the corrupted pattern. We'll look at this after every 10. There it is. All right, so we got it. Let's do it again. All right, so let's put in pattern 4, 0.3, probability of flipping, 10 iterations. Still got 3. Okay, let's see. One more time. All right, we'll do pattern 4, 0.3, 10 iterations. Okay, so we still got 3. And actually looking at that, again, that's kind of hard to tell that that's the number 3. You might actually think of that's a 2. I can kind of see a 2 in there. So let's just push it up a little bit. I feel like if we start with a 3, and let me go up to a 35% chance of corrupting it. Still kind of looks like a 3. I don't know if that's going to go to a 2. I'm trying to get this thing to go to a 2 because the 2 should be a fairly nearby basin of attraction. No, we're back to 3. So actually, I'm not successfully getting to 2. I thought that by picking a pattern that had a fairly high inner product with one of the other patterns that we would tend to, when we had an error, would tend to go to the 2. Although we actually haven't gotten an error yet, so bear with me. I've often mentioned, for me, this is my video gaming. I know that the young people these days are all into the video games on the net and what is it called, massive multiplayer games and stuff like that. Well, I can kind of do this kind of stuff forever. These are my video games. All right, so let's try. Going to do the same thing. Still like the number 3. Let me go ahead and corrupt it by 40% since we know that tends to give us some pretty good errors. It kind of looks like a number 2 to me. In fact, that looks more like a 2 than a 3. So maybe we'll get to 2 this time. And what are we going to get to? Well, we got to a false memory. So there's a final state. It's a steady state. And it's kind of like the number 4, but not quite. But still, it looks like 40% is kind of the threshold for not converging, and so we can get a sense of the size of the basins. And so the basins are about 35 to 40% in diameter, and I know that's kind of a funny unit of measure, but basically, even for a 35% corruption of the input pattern, we were still converging on the correct memory, but by 40% we're now converging, not on other fundamental memories, but actually on these false memories. And there are a lot of false memories. In fact, we can even predict how many false memories there are. So it turns out the storage capacity of a Hopfield neural network is really simple to estimate, because the number of fixed points is equal to the number of eigenstates that are part of the matrix. And so since the size of the matrix is n by n, then it turns out that there's going to be n eigenvalues, n eigenstates coming out of that. But if there's only m fundamental memories, then it means that there's going to be n minus m false memories. And that's actually a pretty big number. So for the Matlab demo that we just ran, it means that our state vector was 120 pixels long, and we only had 8 fundamental memories. And so it means that there's actually about 112 false memories buried inside of that Hopfield network. Now, if the corruption of the input isn't too bad, you really don't get to those. There is this basin of attraction, and as long as you are within the size of the basin of attraction with your corrupted input, then you will actually get to the ideal memory. And so these 112 false memories occur when you're just getting your error rate is just too high. And then if you're not converging on the correct memory, you're actually more likely to converge on a false memory than on one of the other fundamental memories. And so when you're doing recall, chances are that you'll either recall the ideal memory or you'll recall a false memory. If you do recall a false memory, you actually know it. You know that that wasn't in your storage set or your training set. And so you just run the network again. In fact, that is part of the principle of fuzzy logic. With fuzzy logic, you often will run a program many, many times. And what you do is you sort of use majority rule. If you'll get a lot of different answers. Out of fuzzy logic, you can get a lot of different answers every time you run the algorithm. But you're likely to get the right answer more often than any other answer. And so then majority rule ultimately can tell you that, yeah, that is the right recall. It's actually one of the aspects of quantum computing too. Quantum computing, it's actually technically not fuzzy logic, but it's one of the interesting aspects of quantum computers that when you run a quantum algorithm, you'll often get the wrong answer, but it's on a problem that would normally take a classical computer the age of the universe to find. So once you get a wrong answer, you quickly check it. If it is wrong, then you just run the quantum algorithm again. So these neural nets are kind of like that. You might end up running them many times and then going to a majority rule to decide that you've got the right answer. So there is also a rule of thumb for a sort of a well-performing Hopfield neural network, and we don't really have time to go into that. You did notice that there was kind of like a critical threshold around 35 or 40% error rate where we no longer were converging on the right answer. There are phase transitions in Hopfield neural networks, and so these are like percolation thresholds or critical thresholds. And so it turns out that this rule of thumb is actually based on a critical threshold, that the number of elements in your state vector has to be greater than about 7 times the number of fundamental memories for it to converge easily on correct memories. And so roughly you want n to be greater than about 10m, and so about 10 times order of magnitude more or longer or more elements in your state vector than you have fundamental memories. So we had 8 memories. 7 times 8 is 56, and we had our n was a 120. So actually we were a little bit overkill. We probably could have stored at 120, use the rule of thumb of 10. I mean, we really easily could have stored, let's say, 12 fundamental memories, and we would have still had a well-performing Hopfield network.